is going to try and get the oxygen out, and you should know that oxygen prefers being a gas, but those oxygen atoms bound together in those molecules are going to take up not that much room, because in a liquid all the molecules are quite close to each other. So I've got some well-known washing up liquid in there which is hopefully going to catch our oxygen molecules as we persuade them to leave. So the H2O2 is going to want to be H2O, gets rid of excess oxygen. We need 2 oxygen atoms to make an oxygen molecule. So how many oxygen molecules are we going to make? We're going to get that many? That many? Perhaps a few more. Shall we see? I'll put this at the front in case you can't see there. Yeah. In fact, I think I'll move that back. Yeah. Yes. We got, whoops. That's never happened before. That's actually quite hot. Right, okay, so I can feel that being quite a hot reaction. I'll show you some much more violently hot ones than that in a second. But we saw several things there. First of all, we saw the oxygen came out of solution, but we actually changed it from being chemically bonded in the hydrogen peroxide to being freed. 2 oxygen molecules found each other, became oxygen gas, O2, and then that produced bubbles because the washing up liquids was there to catch the oxygen gas as it came out. The bubbles took up an awful lot more room. They've not taken up quite so much room now because they've cooled down. The amount of the amount of room that a gas takes up depends very much on how hot it is. The bubble is large because the gas molecule is hot, because it's produced a lot of heat in the reaction. That means that the molecules are bashing against the surface of the bubble, and that makes the bubble big. As it cools down, then the molecules don't fly as fast, they've not got as much energy, so they don't bash against the sides as much, and so the bubble contracts. And that's what's happening now. So the amount of space taken up by gas is determined a lot by the temperature, but the main point there is gases take up an awful lot more room than space. I started off with about 200 mils of gas and ended up with like almost 20 litres of volume from the bubbles. So gases take up much more room than liquids, and that's because in a liquid the atoms are in contact, they're sliding past each other but still in contact. In a gas the molecules are flying around, bouncing against each other. That's still going, there it goes. So now that we've talked about oxygen, I think we can move on to another gas. We've seen oxygen going into solution, oxygen coming out of solution. We know that we are breathing in the air. That's essential for us because we need to breathe in the oxygen in order to react it with the food that we eat. There's chemical reactions going on in our body. If you've had lunch, you've got the oxygen that you're breathing in reacting with the food that you eat to produce carbon dioxide and energy. That's where your energy goes. So carbon dioxide is a bit easier to talk about than oxygen. With oxygen we use tricks. We've got the methylene blue detector, oxygen detector. We've got the bubbles to try and catch the oxygen, but it's an invisible gas. You can't touch it, you can't feel it, can't taste it really. Whereas carbon dioxide, all we have to do is cool it down. If we cool it down enough, it turns into solid. And so this is carbon dioxide. This is exactly the same as the molecules you're breathing out currently. It's just that we've taken all the energy out of them so that they lie down next to each other and they don't jump around the room. You have to cool it to minus 77 degrees to do that, which is about as cold as it gets on Earth. Bottom of Antarctica on a cold day will get that cold. So, what's happening to that carbon dioxide? You can see the clouds coming off the spoon. That's because the air surrounding the carbon dioxide is saturated with water, and as that air gets cooled, the water precipitates. So what you've got there is clouds basically coming off the spoon. And the other thing that's happening is it's picking up heat from the surroundings, which means it's slowly turning back into gas. And the weird thing about carbon dioxide, this is solid carbon dioxide, in other words it's carbon dioxide ice. Now if it was water ice and we heated it up, it would melt and we'd have a puddle. But this carbon dioxide ice heats up, goes straight from the solid to the gas, so you don't get a puddle. And that's why its other name is dry ice. So dry ice is just solid carbon dioxide. it's slowly picking up heat from its surroundings. That takes a little while when its surroundings are air, but we can speed that process up a bit if we put it in some water, because the heat transfers that much quicker through water. Like that, and more in there. Don't worry, I'll come round with this in a second, just... Right, so we've got our special effects from the dry ice, ground fog. That shows you that it's heating up much faster when you put it in the warm water, so it's turning into clouds much quicker. But in here I've got some dry ice. That is also turning into a gas, but it's doing so more slowly. I've got a way of proving that. I'm just going to pop the lid on. If I pop the lid on, then it'll still be slowly turning into a gas. That's 2, 3. But because I've popped the lid on, it then becomes a little bomb, because there's more carbon dioxide in there as a gas than can be contained within that little plastic tube. So those little plastic tubes are eventually going to give up and they're going to go pop. And I can't tell when that's going to be, but they'll take a little while, which gives us some more time to play with the dry ice. So, yeah. Put a bit more in there, and then I'll do that. And we'll pick this one up, go on to the bucket of clouds. This is a little bit more Halloween than Christmas, really, but everybody get a good look. You probably find that it's not particularly cold. It's just that the water is saturated with basically instant clouds.